everyone. Just a quick word before we start, and that is that the test, which is the Thursday after Thanksgiving, 2 weeks from yesterday, the material will be chapter 2 and 3 of the notes. And so the topics will be uniform convergence, power series, Stone-Weierstrass, connectedness, and contraction. I don't know if you've seen it, but I put a new homework set on the web that covers the remaining topics. So this will be 7 onwards. I'll need to get a room, so I'll announce that on the web page when I have it. So let me I'll make up a practice test, and I'll get that done this weekend and put on the web page. So there'll be a practice test. I'll put all this information on the web as well. Also, the week after Thanksgiving, Wednesday, I'll devote to review and probably go over the practice test then. Now, for the last couple of lectures, what I want to do is just have a look at a couple of topics that will ease you into 447. So these will not be covered on the test. This is just for enjoyment. I know, it's late in the semester. Try to enjoy them. Okay, so and also Dr. Douglas is supposed to come at 11 today to talk to you about 447. So this will be some assorted topics. The first one that I want to talk about is the subject of LP spaces. So we've met little L1 and little L2. So I want to fill in the gaps, and so we'll make the following definition. So let P be somewhere in the interval 1 to infinity. Then we say that a sequence AN is in little LP if the following sum, absolute value of AN raised to the pth power is finite. So we've already met little L2, which is the space of square summable sequences. That had a norm, which was the square root of the sum of the squares. And there's a similar thing here. We define the norm of a sequence AN, P norm, to be equal to the sum from 1 to infinity, absolute value AN to the P, and then we take the pth root. So when P is 2, this is a familiar situation. This is the space little L2. Now, I'm using this symbol here. We'll use the P norm, and I'll call it the P norm. But we will be careful not to use any properties of norms until we prove them. So ultimately we will see that this is a norm, but not just yet. But it seems foolish to construct some other notation for it and then prove that it's a norm. Well, if you think back to when we looked at little L2, basically it was a norm because of the Cauchy-Schwarz inequality. So there was some depth to it. We had to prove that inequality before we could see that this was a norm. And it's the same situation here. So we will need some inequalities to establish this. But the first thing to do is to show that this is a linear space. So for 1 less than P, less than infinity, little LP is a vector space. This just means that you can add things in little LP and scalar multiply them and still be in there.
Didn't we do P equals 1 on homework or something?
Yes.
So wouldn't it be okay to talk about P equals 1 as well for LP spaces?
Oh, yes, we could. I was, well, there is, one is special, and that will appear momentarily.
Okay.
There's a difference between 1 and P bigger than 1. Okay. Now, scalar multiplication is trivial because if you put a constant in front of the ANs, it will just factor out of this sum, and so 1 is finite if and only the other is. So the real issue is adding together 2 sequences in little LP and seeing that you get another one. So suppose that sigma absolute value AN to the P and sigma absolute value Bn to the P are finite. There are, of course, plenty of such sequences because any one that is 0 after a certain point is certainly in little LP. So we have to apply this to the absolute value of the sum. the absolute value of the sum. That is less than or equal to the absolute value of an plus the absolute value of bn. And this, if you add together two numbers, you cannot get more than twice the maximum. So this is less than or equal to twice the maximum of absolute value an, absolute value bn. Consequently, we can raise both sides to the pth power, and we get less than or equal to 2 to the p. When you raise a maximum to the pth power, it's the maximum of the two p powers. So this is the maximum of an to the p, bn to the p. And now the maximum of two numbers is less than or equal to their sum, if they're both positive. So this is less than or equal to 2 to the p times the absolute value of an to the p plus the absolute value of bn to the p. Now, if I sum over n, what I have on the right-hand side is finite. And so we get that sum from 1 to infinity, absolute value an plus bn to the p, is at most 2 to the p times the sum absolute value an to the p and the sum absolute value bn to the p. And because these two series have finite sums, this is finite. And that's what we need for membership in little LP. So little LP is closed under addition. Being closed under scalar multiplication is obvious, since the absolute value of CAN to the P is the absolute value of C to the P times the absolute value of AN. So we are dealing with a vector space here. Now, in order to get what we want, we're going to have a little inequality. So let P be in 1 infinity.
Didn't we also have to prove that A and B are an element of LP, then A times B is also an element of LP?
No, it's not going to be an algebra.
Okay.
And in fact, that generally won't be true. Okay, so let P be in 1 infinity. And let Q exclude 1 because we wouldn't have this Q. If we have any two positive numbers, A and B, then the product, A times B, is at most A to the P over P plus B to the Q divided by Q. Now sometimes, when you're trying to prove inequalities, if you go at it directly, this would be actually quite difficult. But one can bring calculus to bear on such problems by making one of the numbers in there a variable. So let's consider the function basically what I'm going to do is move everything to one side and change one of A or B into a variable. So I'll call it x. So this will be x to the P over P plus B to the Q over Q minus bx. So what we want here is, and this is for x greater than or equal to 0, and what we want is f of x is greater than or equal to 0 for x in 0 infinity. If that's the case, then we will be able to replace x by A, and that will give us the inequality that we want. So let's compute the minimum of this function. Since P is greater than 1, you can see that it's going to go to infinity as x goes to infinity. And when x is 0, it's going to be b to the q over q. So that's some positive number. So the graph will have some shape like this, as we'll see. Okay, so the first observation is that if b happens to be 0, then this is immediately true, because it reduces to x to the p over p. So if b is 0, then f of x is x to the p over p, which is certainly greater than or equal to 0. So we can assume that b is a strictly positive number. So let's minimize this with calculus. F prime of x is x to the p minus 1 minus b. We set the derivative equal to 0, and we get just one solution. X is equal to b to the 1 over p minus 1. When I take the second derivative, this is p minus 1 x to the p minus is certainly greater than or equal to 0, since p is greater than 1. So that means that at our critical point, b to the 1 over p minus 1, we're going to have a minimum.
Strictly greater than 0, right? Because we assume that b is not equal to 0.
Yes, it'll be strictly greater.
X could be 0.
But x is 1 over b power.
Right, but at our critical point. Okay, therefore, b 1 over p minus 1 gives the minimum value. And we just have to see what the minimum value is. So just return to the original function and plug in b to the 1 over p minus 1, and we get b to the p over p minus 1 divided by p plus b to the q over q. And remember that q was p over p minus 1. So that's q. I'll keep the q down below. And then minus b times x. When I add 1 to 1 over p minus 1, I get p over p minus 1. So all the terms have a common b to the p over p minus 1. So this is b to p over p minus 1 times 1 over p plus 1 over q minus 1. And that is 0. So the minimum value is 0, and so what this function looks like it bottoms out here at b to the 1 over p minus 1. So this is our function of x. Right? Okay, so therefore f of x is greater than or equal to 0 on 0 infinity, and then put x is equal to a, and what we will get then is a times b is less than or equal to a to the p over p plus b to the q over q. So for any pair of non-negative numbers, this inequality will be true. Okay, so to see the relevance of this inequality, let's have a look at the following lemma. So let p be in 1 infinity, and let two sequences an and bn multiply the two series together, sigma AN BN is absolutely convergent and satisfies the absolute value of sigma AN BN is less than or equal to the P norm of AN times the Q norm of BN. Now I'm going to do a special case and then get the general case from it. So the special case is this. Both are 1. Okay, so absolute value of sigma AN BN is less than or equal to the sum of absolute value of AN times absolute value of BN. So to prove absolute convergence, we only have to prove that this one converges. So it's enough to show sigma absolute value AN, absolute value of BN is less than or equal to P norm of the A's times the Q norm of the B's. And that's where we'll use that previous inequality. So by 4.3, absolute value of AN times the absolute value of BN is less than or equal to the absolute value of AN to the pth power over P plus the absolute value of BN to the qth power divided by Q. So let us sum over n to get that sigma absolute value AN times BN is at most sigma AN to the P over P plus sigma BN to the Q over Q. Now we're in the special case where the P norms are 1. So this is the P norm. Well, the P norm has a pth root in it. So if I just have this sum with pth powers, that's p norm raised to the p power over p plus q norm raised to the qth power over q. But these numbers are 1, and so this is 1 over p plus 1 over q, which is equal to 1. And that is the same thing as the product of p norm of the ANs times the q norm of the BNs. Because 1 times 1 is equal to 1. So that's the special case. So we've proved the inequality that we want under the assumption that both the p norm and the q norm are equal to. So the general case we can deduce it from this one quite easily. So first of all, there are 2 trivial cases. So the inequality is trivial if the p norm of the ANs is 0 or the q norm of the BNs is 0. Because then one set of terms will be 0 and the inequality reduces to 0 equal less than or equal to 0. So assume both are greater than 0. So let us write alpha for the p norm of the ANs. So alpha to the p is sigma AN to the p. And beta for the other one, q norm of the BNs. So beta to the q is equal to sigma Bn to the q. Well, if I divide through by beta to the q and alpha to the p, then that sum is 1, and sigma Bn over beta to the p is 1. To the q. So by the special case, which applies to these 2 particular series, I get sigma AN BN over alpha beta is less than or equal to 1. But now if I multiply through by alpha beta, I get sigma absolute value an bn is less than or equal to alpha beta, and those were defined as the p norm and q norm respectively. And so I get this inequality.
Everything that we've been doing has been on little LP. Does this also work on LP?
Yes, it does. But in order to talk about LP, you have to develop the notion of measurable functions and so on. You can make it work on continuous functions. That would be fine. Yeah. Where we already have a notion of integrability. Oh, he is? Okay. That's a good place to stop then. I'll go and get him.
I guess so Michael can hear it.
Okay, so I'll show you its norm on Monday. Oh, hello, one, please. No, that's okay. It's a convenient stopping point. Okay, good.
I remembered that this room was in one of these corners, but I didn't remember which corner.
It's about as far as you can get in civilization.
Okay, I don't know whether Roger mentioned. I'm Ron Douglas. I will be teaching 447 next semester. Actually, I don't remember the time. I think it's Monday, Wednesday in the afternoon at some point. I thought I'd come in and tell you, at least let you see what I look like and say a little bit about what I would do with the course. I will continue using the book Carruthers in the sense that the course will be based on that material. I will take up at the section on functions of boundary variation and the Riemann-Stieltjes integral. I'm going to do that, and I'll tell you why in just a minute. I'm going to skip the chapter on Fourier series, and I'll tell you something why. I'm then going to, but the main part of the course will be Lebesgue measure, the construction of Lebesgue measure, which is probably one of the most important things in real analysis, with applications to not all of the rest of mathematics, but also applications to probability theory and large parts of applied mathematics. Excuse me. We will cover then essentially the rest of the book with the next to last chapter. It's not clear how much time there'll be for the last two chapters. The next to last chapter has to do with LP spaces and a little bit of elementary functional analysis, Banach spaces, and so forth. Important material, but I'm probably going to focus more on the last chapter, which is differentiation theory, which allows one to complete the story about the fundamental theorem of calculus. You might think that by now you know all there is to know about it, but in fact a lot of very interesting things happened at the early part of the 20th century. Now, in fact, let me just say something a little bit about that. The material we're talking about here, well, the material in 446, which has been metric spaces and topology and Rn and continuity and so forth, that material got rigorized toward the end of the 19th century and actually put in this form sometime in the 20th century. The material the Lebesgue measure got constructed in the early part of the 20th century. One of the interesting questions from my point of view is, what was the problem Lebesgue was trying to solve? And one of the things which I imagine Roger's probably told you in 446 is that almost all of the analysis we're talking about in both semesters has to do with the problem of Fourier series. Fourier astounded, well, after you had Newton and all sorts of other people that introduced differential equations and partial differential equations, which described all sorts of physical systems, the question was, okay, wonderful, but if you can't solve them, what good is it? Well, it gives you a nice mathematical model, but if you can't solve the model, if you can't answer questions for prediction, it's really not much use. It's theoretical use, but not practical use. Fourier astounds everybody by basically saying, look, if I write the function as a sum of sines and cosines, the wave equation, the heat equation, all these fundamental equations can be solved. But of course, large numbers of people didn't believe him. In fact, most people didn't believe. This is the early part of the 19th century, 1820s, 30s, something like that. Large numbers of people, and there really wasn't much distinction in those days between mathematicians and physicists and engineers. I mean, at least if you were trying to do things in terms of models. It turned out, of course, Fourier wrote things down, and Fourier interchanged the integral with the summation sign, infinite sums. And people quickly showed that that didn't make sense in many cases. You could give examples for which that didn't work. So, and in particular, it does not work for the Riemann integral. And again, Riemann comes along about 1850, 1860, something like that for the Riemann integral. And what were they doing before that? Well, they were using the notion of an integral, but Riemann's the one who formalized it. But whether formalized or unformalized, in other words, what's the case of Riemann, the question was, could you interchange the integral with the summation? Because if you think about trying to write down using Fourier series, that's the critical question. Well, the Riemann integral behaves very badly as far as infinite sums are concerned, unless you've got uniform convergence of functions, and you almost never do. So the Beggs question was, and he wasn't the only one worrying about this, the question was, can we develop an integral, a notion of integration that behaves well with infinite sums, and that's the Lebesgue integral. And Lebesgue measure is the basis for that. Now you might say, well, okay, if that's important, well, I'm going to skip the section on Fourier series. That's something I would encourage the people in the class to read. And in fact, if there are people in an honors section, that's what I often use to do that. Partly because the semester you don't have enough time to do the rest, all these other things, which come down here. I'm going to do functions of bounded variation and the Riemann-Stieltjes integral, which you may or may not know much about what it is because, in fact, that was the integral that was introduced along the way. That was an earlier version of the integral. But it gives you a very concrete way of defining other measures. Now you might say, well, okay, the Lebesgue measure is most important. But in fact, what one encounters in all kinds of analysis and probability theory and statistics and a whole lot of other places, you encounter other measures. And one of the reasons I like to do the Riemann-Stieltjes integral because there's measures that are underlie that. And it gives you experience for that when you go on. Now, if you go on in a graduate program in mathematics, you will be taking a course in real analysis. You'll be doing what's called abstract measure theory. This forms a very good foundation. If you don't have a foundation like this, you've got all these definitions and these theorems, but you really don't understand examples at all. You don't have any example to think about. This course provides the examples for that. If you're in probability and statistics or that general area, this is almost all the measure theory you'll ever need, and in particular distribution functions in probability theory come back to the Riemann-Stieltjes integral and other things. So, and of course, if you're going on in other parts of applied mathematics or other things, or indeed electrical engineering or industrial engineering, a whole lot of other things, the Lebesgue integral is fundamental. An awful lot of courses in engineering, for example, at the graduate level, assume that you know something about it, and they just simply proceed. Well, that's okay. But what you often find out is that, in fact, if you don't know a little bit more than that, you can run into trouble. Now, eventually you learn it, but of course I think this makes a much better order of things. As far as how, in other words, I say, the course will be based on the book. That means I will lecture. I'm not going to repeat the book. I'm not going to cover everything. You're going to have to read it and follow the lectures here. I will also be asking questions in the class of people, just basically going around the room and make sure we understand the things we're talking about. There will be a homework assignment every week. It will, almost all of the problems, maybe all of them, will come from the book because Carruthers has a good set of problems. I don't always like everything that Carruthers does in the book, but I don't, when I give a course using a book in this sense, I don't fight with the book. In other words, I don't spend all my time telling you what's wrong with the book, unless it's absolutely necessary. But I will use the book for two reasons. One is that if you're in this class, you presumably already own the book, and I don't want you to have to go out and buy a second one. But the second one, it's a reasonable book. It's a reasonable approach, and it's perhaps a little bit wordier than it needs to be, but a lot of books are like that these days. So there'll be a homework assignment. There'll be either one or two midterms. The midterms will be on whatever ones we've done up to that particular point. There'll be a final exam. They'll be like this. I do not give exams in which I ask you for the definition of something. I give exams in which I'll either give you examples or ask for examples or ask you to prove very simple things as far as those things are concerned. The question I'll be asking is, do you understand the definition, not can you repeat the definition? Well, I'll just say something about this. At the level this course at 447 is, I would assume, unless I've got an unusual class, and that's possible, that the average grade in the class will be a B+, possibly even an A- or something like that. That doesn't mean that's guaranteed. If everybody comes in and doesn't work or doesn't do whatever else, I'll give the appropriate grade. If it turns out that but what I'm saying, I start out assuming that that's roughly what the grade will be in the course. That's not promising anything, but it's just kind of telling you my expectations. It is a rigorous course, and it is a course in which we prove theorems, in which problems in the course will be asking to prove theorems. I will not ask you to prove something difficult on a midterm or a final exam, because you won't have time to do it. And I'm not going to ask you to remember a proof. I'm going to ask you to understand the proof and be able to use those ideas in doing simple things that are like it or based on it or something like that. I can't think of much else myself, but does anybody have any questions about the course or how I'm going to run the course? Okay, well, I think I've told you why, from my point of view, what I think is important in the course, and why I think it's an important course for a lot of people, and where it fits in your curriculum and what it's based on, and how I'm going to run the course, and I hope to see most or all of you next semester. Thank you.
Thank you.
I think that's it for the day. I don't think Roger's coming back.